Lesson 84, degree of equations and solutions to systems of equations. All right, in this lesson, we're not actually doing a whole lot of work. Instead, we've got a lot of different terms that we're going to use to implement in solving different things. So first, let's talk about degree of equations. All right, when we talk about degrees of equations, we're talking about two different things. We can either talk about the degree of the equations themselves, or we can talk about the degree of the terms in those equations. All right, so let's talk about a degree of terms, first of all. All right, the degree of a term is this. It is the sum of all of the exponents of the variables in the term. All right, so we take all of the variables, we add all of the exponents. Doesn't matter if the variables are alike or unlike, but we add all of the exponents, and the sum of those exponents is the degree of the term. All right, so for example, the term 2. All right, term 2 has no variables, therefore the exponents are 0. So this is a 0 degree term. All right, if I had something that was x cubed, all right, well, the only variable is an x, and the only exponent is a 3, so this would be a 3rd degree term. All right, if I had an x squared m n k. All right, we're going to take all of the exponents. So this has an exponent of 2, m has a 1, 2 and 1 is 3, n has a 1, 3 and 1 is 4, k has a 1, 4 and 1 is 5. So this would be a 5th degree term. All right, so we are just adding the exponents of all the different variables. All right, so you can have a 0 degree term, a 2, a 1, 3, a 4, etc. All right, so that's the degree of a term. All right, let's talk about the degree of a polynomial. This is degree of an equation. All right, so when we're talking about degree of a polynomial, we first have to look at each of the individual terms, and the degree of the polynomial would be the same as the highest degree term. All right, so if we had a polynomial expression that said 3x cubed plus 2x squared plus x equals 0. All right, the degree of this entire polynomial would be 3. All right, because we look at each term. This term has a degree of 3 by itself. This term has a degree of 1 by itself, and this term has a degree of 1 by itself, and we always go with the highest. All right, so this would be a 3rd degree term. If we were to look at another one, let's say we had xy plus 5. This expression, okay, this is a polynomial, it's a binomial. This one would have a degree of 2. All right, this would be a 2nd degree. I'll put up here that this one's a 3rd degree. This would be a 2nd degree term because this term is a 2, and this term, since it has no variables, is a 0. So we always go with the highest. All right, so that's degrees of polynomials and degrees of expression. If you want more information on this, there's a paragraph in your book on page 346, but that is all we are going to do with degrees of equations. All right, I think there's a couple of problems that we're going to do in class that just ask you simply, what is the degree of this polynomial expression? All right, the next part of this lesson is kind of what we want to stick on and get into. This is solutions to systems of equations. All right, we have talked a lot about systems of equations. These are the, you've either got linear expressions where we have to graph the line, find the slope, find the y-intercepts. We've talked about systems of equations where we've got x and y values where we have to solve by either substitution or elimination. But when we're looking at systems of equations, which is what we're going to focus on today, okay, when we've got two linear equations being graphed in the same coordinate plane, there are 4 different types of solutions that we're going to talk about. All right. The first name given, we can have a consistent system. All right. If we have a consistent system of solutions, all right, this means that one solution is common to all equations in the system. All right, so we have one solution that's common to all of the different equations in the system. For example, when you graph a line, just one line by itself, you can substitute any x value into an equation and have many different y values, all right? But when you, so one line would have an infinite number of solutions. But when you graph it, there's only one ordered pair that is going to satisfy both equations, all right? When one solution satisfies both equations, okay, meaning the lines cross at one point, it's a consistent system. All right, so if we want to write underneath this that the lines cross at only one point, that would be helpful for us to determine if it's consistent or inconsistent. All right, so the lines cross at only one point. All right, the opposite of a consistent system would then be an inconsistent system. All right, in an inconsistent system of equations, there is no solution. All right, so in an inconsistent system, this would be 2 lines that do not cross at all. All right, another kind of system is a dependent system. All right, in a dependent system, one of the equations contains all of the solutions common to all other equations of the system. All right, we're going to write this down and then I'll kind of explain what I mean by this. But one of the equations in the system contains the solutions common to all other equations in the system. All right, when we're dealing with dependent systems, in these dependent systems, one of the equations contains the solutions common to all other equations, meaning they have the same graph. All right, so we can simplify this as being the same graph. One doesn't depend on the other, they contain the same solutions all the way across the board. All right, and then of course the opposite of a dependent system would be an independent system. All right, an independent system would, it would just be a different graph, all right? So not relying on the same points, it looks like a different graph, all right? So it's just the opposite of a dependent system. If you have space up by an inconsistent system, all right, we said an inconsistent system said that there was no solution, meaning they don't cross. All right, an example of this would be when we're just looking at equations of lines. If you were to look Inconsistent systems often have the same slope, but they have different intercepts. In an equation that has the same slope, okay, they're going along the same pathway, but if they have different intercepts, they're never going to cross, meaning they're running just side by side on the graph. That would be what is called an inconsistent system, where they never cross at all. All right, now, when we're talking about this, when you're talking about solutions of an equation, there are three possibilities. All right, we're going to talk about those possibilities. All right, so in graphing a system, the first possibility is that the lines cross and have one point in common. All right, if the lines are going to cross and they have one point in common, okay, two lines crossing, and we said that if they have one common solution, according to the other slide, they would be considered a consistent system. All right, so when lines cross and have one point in system, they are consistent. Okay, lines are either going to be consistent or inconsistent, dependent or independent. So they are going to have two qualifications. All right, so lines cross and they have one point in common, meaning it's consistent. Okay, there's one solution common to all equations in the system. But are they dependent or are they independent? Do they have the same graph or do they have a different graph? That would depend on if they if they look the same. If they are crossing, obviously they're not the same graph, and so they're going to be independent of each other. All right, so when lines cross and they have one point in common, they are inconsistent and dependent. The second option you can have is the lines overlap. Because the equation describes the same line. All right, if the lines overlap, and we're talking about the same line, obviously every solution to that equation is going to be true for both pairs. All right, so if I have a line that is being graphed in the same, it's going to be a consistent system. All right, all solutions are common. All right, so it's going to be consistent. And then we already determined that if they are dependent systems, they're going to have the same graph. Well, if my lines are overlapping, obviously they're the same, so it's going to be a consistent dependent. All right, so when lines cross and have one point in common, they're consistent and independent. When the lines overlap, because the equation describes the same line, they're consistent and dependent. And the final option is the lines are parallel. And have different intercepts. So there are no points in common. Okay, if there are no points in common to the line, that means that there is not an ordered pair that would be able to satisfy the equation. If there is no solution, it's going to be an inconsistent. And since there is no solution, they're not going to be dependent of anything else, so they're also independent. All right, so this gives you the three options and tells you kind of what category they fall into. I'm going to write a system of equations up on the board, and what I want you to do is see if you can determine if they are consistent, inconsistent, dependent, or independent. All right, so here is your system of equations. We have 3x minus y equals negative 2, and 2y equals 6x plus 5. All right, I want you to determine, is it consistent or inconsistent, dependent or independent. And the best way to do this, not necessarily to even graph, but in order to be able to sell anything at all, you're going to need to be able to put it in y equals form, all right, and determine the equation of the line. So go ahead and try that, make your determination, and we will talk about it when we come back into class.